You'll remember this is where we left off last time, right? The program counter, and we were going to start using the program counter to, help us run a program. And I made a big to-do about, in the previous one, because we were making use of RAM and we kind of programmed RAM beforehand. And by programmed, I mean assigned data into the RAM addresses. I didn't really need to add any data to the system as it was running, but I kind of did because I had to manipulate the input toggles for the address of the RAM that I wanted. Where now I'm going to see if I can do this without touching those input toggles at all. All right? I'm still going to manipulate the control signals. When I say, it's still running. When I mean this part right here. I don't want to touch this. I'm going to have to touch this. But this part I don't want to have to touch. And we saw last time that we also had like a program that we're going to load into RAM. So when I hit run, if I go here, we should already have F and 4, right? I want to add 15 and 4. Okay? Cool? Cool, cool. Now we also saw in that hex file, I also had like a 0 and a 0, whatever. That doesn't really matter because digital pads this out with zeros. In reality, RAM wouldn't be starting with a bunch of zeros. It would have a bunch of nonsense in it. But, we're a little lucky. Okay, so now let's think about this for a second. If I have the program counter is currently holding a 0. Now look, when we hit run, again, the address register and all the registers, they start with the value 0 in it. But in practice, they don't. I mean, the program counter won't because, well, actually, really, it shouldn't start with 0. It should start with an arbitrary value, and sometimes it needs to kind of like reset. But it starts at 0 for our needs. But the address register, when we hit run, the contents might be a bunch of nonsense. In digital, it won't be. It'll be 0. But in practice, it would be. So I'm going to run this as if like, okay, I don't know what's in there. So what am I going to have to do? The program counter contains the value 0. I need the data from 0, and I want to put in register A. So what do? I go down here. This is getting tough to do. I want program counter out and RAM, address register in, okay? So clock pulse, great. I should move the clock down here, shouldn't I? All right, so 0's on the bus. Ooh, are these all Z? They're not Z. I should set the, no, what was I thinking? Okay, let's start again. Did we see what happened? I was outputting from the program counter and then I tried to manipulate. All right, let's try that again. Run. Okay, set these to Z. And you know what? No. Let's just do this. We don't need it anymore, I don't think. There. There's no more input, okay? At least that's the goal. Can I do this without using those inputs? Okay, run. All right, so now there's no concern. This would be so much easier if I could use a mouse. Okay, program counter out, address in. Go up here, pulse. Okay, cool. So this now has a 0. Good. Okay. So now we'll turn these off. And now I want RAM out, A in, right? Now, here, let's do this. Okay. Clock pulse. Okay, cool. Now, turn these off. 15 should be an A. Let's just check. Yes, perfect. It's an F. All right, now, remember, the program counter is supposed to hold the address of the next thing. And it's still 0. It shouldn't be 0. We really should program counter enable clock pulse. Okay, there. All right, and so now it should be 1. Perfect. Okay. So what's the state of the system? All right, the address register is holding a 0. The program counter has a 1. A has 15. Now what? Well, I want the value from address 1 to go into the B register. So how do I do that? Well, I have to update the address register. So program counter out, address in, clock pulse. Cool. All right, and now I want RAM out, B in. Now, turns out, let me ask you a question. Let me ask you. Can I do program enable right now? Program counter enable, pardon me. If I enable the program counter right now while sending data from here to here, program counter enable and the program counter's ability to count is entirely independent from the data bus. Meaning I could actually move the data from RAM to B, register B, and increment the program counter at the same time. I can do that. It's safe, which is cool. So let's just do that, program counter enable. Cool. All right. Clock pulse. Perfect. So as of now, we should have an F and a 4. Perfect. So I could do something like let's say ALU out and output register in, clock pulse, and there we go. Fantastic. Maybe I should have incremented program count to, I don't know, whatever, but 19. So we did the exact same thing we did last time without needing any input toggling. I didn't need to input any data as in like operands, things that I'm going to apply addition to. I also didn't need to input any information regarding any memory address because it was already stored in the system. Now, let's say, for the sake of an example, I want to do this again but do subtraction. Okay? All right, well, first of all, you might say, well, that's easy to do. Just turn that on. And clock pulse. There, now it's 11. Great, fine, fine. But let's say, for example, it wasn't that easy. Let's say I have to go back and get information from memory address 0, right? Memory address 0 contains F. I want to put that into A. I know it's already in A, but let's say we have to go back and do it again. All right? And I want to take the thing from memory address 1 and put it into B. Again, it's there, but we're pretending it's not. The problem right now is the program counter is, what, 2? So I'm kind of stuck. But you might remember that the contents of memory address 2 is a 0. Okay? So how about this? Okay, let's turn these off. Let's say, what is currently the contents of the address register? A 1? It's still a 1. So let's take the contents of the program counter. Because by the way, if we go, pardon me, and we look, no, that's the 7-segment display patterns. Where's the, where's the output program counter? Program counter. RAM 15.4. Like, I know it pads it, but like I added some zeros there just because. So, you know, I put a 0 in there intentionally. Okay, so let's take the value of the program counter, which is 2, So program counter out, address register in. Clock pulse, it's now a 2. So now let's do RAM out, program counter in. What will the program counter now be? 0. We're looping. Program counter, 0. Perfect. Turn those off. So now I can now say, okay, look, program counter is 0. So program counter out, address in. There. 0. Whoop. RAM out, A in. And let's increment program counter. Clock pulse. Okay. Address in, program counter out, because program counter should now be 1. Let's just verify. Yeah, it's a 1. Clock pulse. So address now is a 1. We can then say RAM out, B in. Clock pulse. And then we can do whatever we want. The point is, because I can update the value in the program counter, I can like loop. In fact, I can do more than loop. I can really kind of jump anywhere I want in RAM. I could have, if I wanted, jumped to memory address like 13. Not very helpful in this particular example, but I can jump around. But you know, clearly we can like loop. I was able to go back and get the data already passed over, which is pretty cool. And you might say, well, how come this is outputting 11? You didn't do the subtraction yet. Yeah, I know. I did it before, and I latched it into the output register, and the output register was latched, and it never changed, so it's still showing us 11. Any questions about what we just did? I hope you really kind of see the big deal now. Is, like, maybe you see, okay, yeah, great, he was able to do the programming, but now he didn't need to input the data, whatever. That's kind of a big deal. Before we eliminated adding like explicit data, now we eliminated the need to add that like ancillary data, like the addresses, which yeah, it's data, but it's data specific to like how the computer, like it needs to know where it is in RAM. It was more about the system as opposed to what data I'm actually like doing addition on. Hopefully you can kind of see that. But we're really trying to like alienate ourselves from the system as much as possible here. The system is becoming more and more self-contained, and this is a pretty big deal. But like we were talking before, we are still missing a very big key aspect of any computer that we're used to working with. That like in our context at least, where we are writing programs and we say run in your computer and goes and does everything. At no point in any of your programs that you've written so far where you've ever hit run, and I'm talking like, let's say Python, you hit run and it starts doing its thing, other than you adding like input, if it asks for input, you're not going and manipulating any control signals or anything like nonsense like that we have to be doing here. It's because the manipulation of those control signals is how the computer actually does its thing. But there's no intelligence yet on having the computer manipulate its own control signals, right? We had to do it intelligently, but systematically. There was a pattern. Everything we wanted to do has a very systematic strategy. There's an order of how we want to manipulate the control signals, and it's like it's the same every time. You want to move something from RAM to register? Okay, how do you do that? Well, get the address, output from RAM into the register. The control signals are the same every time. It's the data that's different, right? If you say, go load data from some register, go load data from some memory address into register A, you need to know the memory address, but that came from like the program counter. The control signals are get the information from the program counter into the address register, RAM to A. The control logic was the same. So we're getting really close to finding some patterns we can really start to take advantage of. Any questions about any of that? All right, what am I saying here? Okay, we can load it into memory. Yeah. Okay, whatever. This program. Okay. So I do mention here, so a moment ago I just said, hey, when we're moving data from RAM to the register, I can also enable the program counter at the exact same time, right? Could I have done it even earlier? Could I have said, move the data from the program counter, let's just go here. Can I move the data from the program counter here into the address register and also increment the program counter at the same time? Take a moment and think about that. Maybe we can. Think about that for a second. Is the question clear? Raise your hand if you think it's fine. Raise your hand if you think it's not fine. Raise your hand if you think, I don't know. It's kind of in the, And when I mean I don't know, I don't mean like, I don't know. I mean, ooh, I can see why, maybe? Yeah? That's what you mean. Okay, it wasn't, okay. So let's think about the potential issue here. Okay, so we've got data's here, okay? When I set the control signal for the program counter out, this signal turns into whatever this is. So let's say it's a 0. Okay, so this becomes a 0, which means there's a 0 right here. A 0 is waiting right here. And as soon as there's a clock pulse, it gets latched in. The instant. Okay? But as soon as there's a clock pulse here, Cin will also count. So the question is it possible to have this count, thereby changing this from a 0 to a 1 before this increments, or before this latches, right? If everything is perfectly synchronized, it should be safe. But in reality, there are physical limitations to all of this. There is a delay. Now, I'm talking on the order of like nanoseconds. Fractions of fractions of fractions of fractions of seconds. But there is a delay. But like, would the delay from this incrementing to go through here and out here, all the way down here, back to here, could that ever? And the point here is, maybe, I don't know. Could it be a problem? I don't know. It's something to be aware of. Maybe it's fine, maybe it's not. But I think we can see, like the point I'm making here is we should see that this could be a problem. Let's see what happens in practice. Could I say program counter out, address in, and program counter enable? Okay, so right now, program counter out is 0. Right, there's a 0 here. Okay, that's still a 0. There's a 0 right here. When I clock pulse, if everything worked fine, this should store a 0, not a 1. This should be a 1. And in fact, this whole signal line should be a 1 because output enable is still on here. So this should become a 1, but this should become a 0. It already is a 0, but the point is it shouldn't turn into a 1. Because if it does turn into a 1, that means somehow, despite the synchronization of the system, if it does turn into a 1, that means this somehow became a 0 to a 1, and that value of a 1 was able to get here before this actually latched in. Let's see. What do we think? Who thinks it's going to be safe? Why? Give me a better answer than, I don't know. It just feels like it. Well, let's see. All right. Let's go turn everything off. So if it worked here, this should become a 1. This is a 1. Yeah, it's a 1. Good. This is a Z. Great. But the big question is, what value is on this line right here? Raise your hand if you think it's going to be a 0, really high. Come on, commit. I don't want, no, put a hand up or not. You know, really commit or not. Oh, wait, this should be a Z? Z? Yeah, and 0. Yeah, right? Hey. Now, right, you'd think so. But the point I'm making here, now actually I got to double check what I say in my note. Do I say in practice, it may be problematic. So like it may be. Now, really, really, really in practice, would it be a problem? There would have to be some really crazy delays in this latching. Because there's going to be delays in latching, but if somehow the delay of having a value go in here, there's a register in here and a counter in there, right? So there's actually a lot of components in there. Sorry, a register and an adder. So the delay of latching into the program counter's register and going through the counter, oh, I guess really the delay of going through the count, well, the value is already there. So the delay of going through the program counter's register to increment, through the output driver, through the signal line, to the input of the address register, if that delay somehow is less than the delay it takes to latch into the address register, you probably need a new address register, okay? But these types of considerations, like, anyone in here like overclock your computer? Right? If you ever do something like that, but you know there's a limit, why can't you just crank it? Why? There's physical limitations that are all related to the same idea of like, well, because like when you're going at like, let's see here real quick. Delay in tariffs, nice. Delay in French, yeah, there we go. What do I want to look up? Delay in transistors. Well, yeah, but how long? It's going to be like nanoseconds, okay? How many nano in a second, right? Times 10 to the 9, times 10 to the 9, okay? So that's like a billion, right? A billion, so 0, 0, 0, 0, 0, 0, 0, 0, 0. That's a billion, right? Right? How many, like, what's like the frequency of your computer? Like, who knows, like, who can ballpark the frequency of the computer that they're running right now?
My computer's like
3.5 gigahertz, right? So 3.5, it should be an uppercase G, but whatever, and an H, but whatever. So how many, well, okay, how much is a giga? 1,000? A million? I think a mega is a million, isn't it? Kilo, mega, giga, right? That's a billion, right? So that means you're having 3,500,000,000 things happening a second, right? Right? Yeah? Hertz means per second, right? You're going to have 3.5 billion things happening a second. And you might be wondering, why are gigahertz? Well, look at that. There's like literal. You see? The transistors can only move so fast. Having this go any faster, like we are hitting the limitations of the clock speeds because of how fast the physical solid state matter we use for our transistors and crap to work. Like we can't go faster because otherwise the delays are just, it's too slow, right? Imagine like saying like, okay, signal go high. Okay, well the time it takes for the signal to go high, right? This might be like 0.5 nanoseconds or something, okay? But if I say, okay, go high, but in less than I say go low, well, this signal hasn't even changed. Like this signal can't get processed before we're changing the signal. These delays actually create a bit of a problem. And it's related to this type of stuff, okay? So we have to be very careful about synchronization. I don't know about you, I think that's kind of neat, right? It kind of gives you a sense of what these limitations are. Look, there's a lot more to it than this, right? I'm just giving you a very 1,000-foot view of it. But we're going to have problems. Any questions about any of that? Happy, sad? If you overclock it too much and your transistors can't keep up, your computer that's overclocked ain't going to work right. You're going to have a lot of problems with it. Things get corrupted and just instructions can't get run. All right. So there's that warning. So another way to kind of protect against that situation, which really wouldn't happen in digital, but we could protect against it by, well, just don't increment it at the same time. Don't increment the program counter at the same time that you're trying to get the data out of it. That might make things a little safer. All right. What's interesting is that no data needed to be input into the system. At runtime, this addition happened without needing to manipulate data input toggles. All the data the system needed was contained in the system, although the control signals still needed to be manipulated manually. All right. Instructions and microcodes. Here we go. You ready? Strap yourselves in. Here we go. It's now time to start talking about how do we make instructions for this computer? We executed the instructions, but how do we tell the computer, like, okay, go add. Now do it, right? Instead of us going like, this signal, clock pulse, this signal, clock pulse. How can we just say add and then have it do it? That's what we're working towards. And working towards this is that we got a long way to go, okay? We have to talk about instructions, control logic, and then we can start to actually do programs. So we've got a couple of topics to go through before we can really even see what this means. So strap yourselves in. Okay. RAM, so far, we only used it to control data. Computation has been performed on the system, though, but RAM only ever stored data, no instructions. We were carefully manipulating those control signals to do very specific operations, but those control signals were, like, to me, I find it kind of easy. You want to get data from RAM into register A, how do you do it? Output RAM, put it into A, right? Like, it's pretty straightforward. And there is a systematic, clear way into how to do everything. It's going to be the same every time we want to do it, the control logic. So we were able to do things like reading and writing to RAM, performing arithmetic, outputting values, looping. There we go. We could have had more fun with the program counter example. I could have outputted the data from the ALU to memory address 0, whatever. We could have done a lot of different things, right? We still could have played around without ever toggling any inputs. But we did all these things, right? So now that we realize this, it becomes possible for us to say, like, well, okay, we were able to read and write from RAM, perform arithmetic. You know, I did addition, I did subtraction. We output values to the output register. We did some looping. If these are all things we can do, like, what else can we do with our system? We can start to think what set of well-defined instructions we might want our system to be able to do. We've done some. What else can we do? What all might we want to do? Now, let's talk a little bit about the constraints of our system. As we go, we are working towards making a Turing-complete computer, which is a fancy way to say that, like, we could do anything with this thing, okay? It could play Doom, although ours can't, not because it is computationally lacking, but because we have 16 bytes of RAM. And I think you need a little bit more than that for Doom, okay? So our limitation is not based on, like, at this stage, we have a computational limitation that we're going to work towards fixing as we go. But the limitation of the computer is going to be the fact that we have an 8-bit bus, 16 bytes of RAM. Like, that's our constraints. So the designers of the computer, us in this particular case, we get to decide what instructions we want to include. What can our system perform? But what are our limitations? We have an 8-bit bus. And only 4 bits of those 8 bits can be used to address RAM, meaning we have 16 bytes, right? You can try to make it sound fancy by saying, well, what's 16 times 8? Who can tell me? 128. We could be like, oh, it's 128 bits. Sounds better. But it's still only 16 bytes of RAM. Okay. So the system, careful functionality, it is limited to the fact that it's an 8-bit system. RAM is byte addressable. Actually, that's not really, that's a good thing. We like having byte addressable RAM. We love the ability to be able to get 1 byte of information at a time. But the point is we have an 8-bit wide bus. So the information on the bus can only ever be 8 bits wide. This information includes data and instructions. So I have 8 bits that can represent data, any value between 0 and 255, or negative 128 to 127. But that also includes what the instructions can be. Instructions have to fit into 8 bits. Now, what the instructions are and how the system deals with them, we'll talk about shortly. For now, consider that for our system, individual instructions will be made up of 2 parts. This is how we're going to do it. We could do it in other ways. Like, raise your hand if you finished, or at least almost maybe kind of finished assignment 3. Okay. So for those of you that have, and for those of you that will in the next week or so, when you say like think of when you had 3 bits for an operator, right? 3 bits for a source, 3 bits for another source, and 3 bits for a destination, right? We had like OP, A, B, and like a destination, right? That bit pattern, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, is 12 bits long. Actually, like that's like an instruction. That could be like add the contents of some register to another register and store it in another register, right? That's a 12-bit instruction that has several parts: an operator, an A, a B, and a destination. What we're going to be doing for our ESAP system is much simpler. We're going to have an operator and an operand. It's only going to have two parts. The operator, which specifies an operation. Now, I want to try to be careful that when I say instruction, I mean operator and operand together. The operand is part of instruction, and the operator is part of the instruction. So the operator would specify an operation, something like add, load, output, jump, halt, whatever. So the operator says what we're going to do, and the operand is effectively like an argument for that operation, right? Load what? Output what? The operand is where we specify. Cool? So you can think of it as simply like, well, this is a function, and this is its argument. But our functions are only going to have like a very special, like one argument each. Where in this example in the assignment, you would have like an operation followed by 3 arguments, which was kind of neat, right? Ours, far simpler. But in spite of its simplicity, like you can go out there and find instruction sets for popular real processors that are going to be more like our ESAP system or more like that system, but it's all kind of, one's not necessarily more powerful than the other computationally speaking. In fact, they aren't. They will be computationally both capable of doing the same thing. You can play Doom on both. All right, so for example, imagine an instruction where we want to say load data from a RAM address into register A. So the operator could be like load data into register A. The operand is the RAM address. What data? From where? So load the contents of load the contents of memory address 15 into register A. Great. That would mean for the system to go, okay, we need to somehow take the value of the operand and put it into the address register, output from RAM to the A register. Like, you know, like that's what that would mean. So, yeah, we need a way to encode an operator and an operand. But we have 8 bits. So we only have 8 bits to somehow encode 2 different pieces of information. We need to decide how many bits for each part. And the decision has huge implications for the system. Should I have 2 bits for the operator? If I do, I can only have 4 operations, right? Because each bit pattern needs to uniquely identify an operation. If I have 3, I can have 8. If I have 4, I can have 16. If I have 5, I can have 32 instructions, operations. But as I add more instructions, I reduce the amount of room I have for my operand. Now, we already kind of painted ourselves into a corner where, look, we have 4 bits to specify a RAM address. We should have 4 bits for the operand, right? Load the contents of address, whatever. So we'll have 4 bits for our operand by the design of the system, which leaves us with 4 bits for the instructions. What I mean is, we can only have 16 unique instructions for our system. But what those instructions are, and how they do what they gotta do to do what they gotta do, is entirely up to us. We are inventing it. It's common, especially in technical fields like this, where when you learn these things for the first time, it's common to think that this information was handed down by the gods on stone plates or something. Where you're like, this is the way it is. But you got to remember, someone somewhere invented this stuff. We are inventing this stuff for our system. So we get to invent what instructions do we want, and we get to say how those instructions happen on the system, assuming the system is capable of doing it. As of now, we can't have an instruction for multiplication, and we'll see why in a second, because our system just can't multiply. In hardware, at least. We'll be able to multiply in software, but that's a problem for later. So, if we have the most, you'll also notice if we go to the ESAP system, what we designed, it was always the least significant 4 bits that was coming from the program counter and also going to the address register. So the least significant 4 bits will be the operand, and the most significant 4 bits will be the operator. So we have 16 unique operators, and for each operator, we could have 16 unique operands. This is perfect because we have 16 unique memory addresses. It's perfect. It's almost like this design was kind of intentional. So this is the idea. With 8 bits, I've got 4 for the operator and 4 for the operand. That's how we're going to do it. We haven't talked about what those operations are going to be, what the instructions are going to be, how we're going to do them. That's fine. Right now, we're just thinking within the system, how could we make this work? That's what we're evaluating. So like I was saying, we could have 3 bits for the operator or 5 bits for the operand. Like we have all these options that we could do. And these are always like trade-offs. We always okay, we could have more of this, but less of this. More of that, but more of that. And what's better? It's entirely up to us. We are inventing it. Does it serve our needs? Do we want more or less flexibility with the number of operators at the cost benefit of how much address space we have, for example? As previously mentioned, more details to come though on how we are actually going to encode the instructions, what these instructions are, and so on and so on and so on. The reason that it's open is there's no real set. We get to invent it. So we'll get to inventing what we want in a moment. We just need to understand our constraints. There's also this idea of microcodes. Have I talked about microcodes before? I think I brought it up, but it was really quick and with no context, so it probably wouldn't have stuck. You will notice that, look, when we were doing some of the operations, like load the value, you will notice that doing 1 unit of work, and the number of clock cycles, 1 unit of work, we really get to define what 1 unit of work is, okay? If I were to say, I'm trying to think of a good example. I suppose what I mean is, when we think of all those tables, think of all the times we hit run on the simulator and we were moving things around. In order to be I want to add 2 numbers together, you saw that there were a lot of clock cycles were required to do that, right? We had to configure the control logic, pulse, configure it again, pulse, and there. Now our data is where we want it, right? It took several steps. Now, when I say unit of work, we could say a unit of work is move data from the program counter to the address register. We could say that. That is a very low, that's very low level. We are defining instructions, and instructions are a way to add another layer of abstraction to our system. We want to interface with our system at the level of instructions. Now, what should those instructions be? Again, we are defining this. But do I want my instructions to be at a very high level where I've got these crazy functions that do a lot of low-level things? Or do we want our instructions to be very low level to mean 1 very basic unit of work? Or do we want it to be somewhere in between where it's load the value at a specific memory address into register A, right? What happens? Well, we need to get the value of the memory address that we want to load into the address register. Then we need to get the value from the address register into the RAM, which it does that automatically through the little address bus, and then the contents from RAM to the A register, right? That's a reasonable unit of work. Sending something specifically to the address register, we could make that a unit of work. We could make that an instruction, but that's very low level. And by making things more low level, you know, like that's going to make our code very verbose, which is fine, but you know, the point I'm trying to make here is when we're starting to define instructions, how specific or general do we want our instructions to be? We have a decision to make. We can be like, write an instruction to, I'm having a hard time trying to come up with an example because of how simple our system is, but you know, we could write an instruction to be like add 15 and 4 together. And immediately we're going to say like, okay, well that's not very general. You're right. Always those two numbers, that's stupid. In the same way that, you know, we're defining functions in like Python, right? You want them to be general, but you want them to be sophisticated enough that like when I go and I write a function, I want it to do several steps. I could do each step individually, but you know, kind of the point of writing a function is that you kind of abstract several instructions, right? Now, look, when we're talking about making the instructions for our architecture, we're not talking about writing functions yet. We're talking about like the lowest level of thing, like what our instructions going to be. But our instructions can be as simple as move these bits around, or they could be like get the contents from this memory address, which requires several steps. Or we can make it more complicated that might require more steps. But then we lose flexibility. It's another balancing game. All of this to say is, if we have an instruction like move the contents from some specific memory address to register A, I have to put that memory address into the address register. That takes 1 clock pulse. Then I have to output from the RAM address that the address register has and put it into the A register. That's another clock pulse. That took multiple steps. And those individual steps and those control patterns, those are called microcodes. The instruction would be like the code, but under that instruction, there are actually a couple of steps involved. Those are called microcodes. Any questions about that? All right, we'll pick up here on Tuesday.